All right, so this part of the lecture is from chapter 2, but this is related with our next lab, which is the lab 7. In this lab, we'll actually learn about a condition which is related to the addition and subtraction. You remember the last lab, which was lab 6, we actually tried the binary addition using binary adders, right? And the circuit can also do the subtraction based on the mood switch. It can do the subtraction and addition. Now, in case of addition or subtraction, the digital circuit uh, sometimes does a mistake, which is called overflow condition. Now, there is actually no way you can fix this condition, fix this overflow condition, but there is a way we can build a circuit which can tell us that the overflow condition occurred or not. That means, because of the limitation of the space, some of the digital operation like the Boolean operation like binary addition and subtraction will always give you the wrong answer. And there is no way you actually can fix it. This happens because of the way we represent the negative number. Remember in the lab 2 and lab 1, when we first talk about the binary numbers, we learned how to represent the negative numbers. In the Boolean operation, there is no way you can use a sign in front of a number just to say, oh, this is a negative number. Instead, we use remember the left digit is for the sign, and which means if the leftmost digit is 0, then we know that this is a positive number. If the leftmost digit is 1, that means a negative number, and that because of that kind of representation, a lot of binary operation will not give you the right answer. And we'll show you example here. So let's say in case of two signed numbers. See, in this lecture, all the numbers that we'll be talking about will be actually signed numbers. Okay, that means we assume that those are signed numbers. Again, as I said before, the binary numbers doesn't have sign. But if the number starts with 1, that is a negative number. If the number starts with a 0, that's a positive number. Okay. Now, for an example, if you recall, this is actually plus 64, because you see here in the left side, this is 0, right? So this is a positive number. And if you just use all the weighted average, remember we use the weighted, we use some weights to calculate what number it is. You know that, right? So we start from the weight here, right? So it's a weight of this position is 1, and then 2, and then 4, 8, 16, 32, 64. The 64 position is 1, so this number is 64. And the next number is 65 because the 64 position is 1 and this position is 1, so 64 plus 1 is 65. So if you just use the binary rules for addition and add these two numbers, this is what you will be getting. And then because of the 1 at the very leftmost position, this number becomes a negative number. Remember, if you recall, all the negative numbers actually start with a 1 because the very leftmost weight is negative. If I just write those weights again, if you probably can recall, it starts from 1, then 2, then 4, and 8, and 16, 32, 64, but the very leftmost one is actually negative 128. So if you have a 1 there, that makes it a negative number. Now, this is actually wrong if you think all the numbers are signed numbers, because when you are adding two positive numbers, there is no way your answer can be negative. But there is no way you actually can correct it because of the negative number representation technique we use in the binary circuits. I'm saying the digital circuit. Same is here. If you look at these two numbers here, these two numbers are negative numbers because they start with 1. And I actually wrote the numbers at the right side. This is negative 127, and the next one is negative 126. If you add these two numbers, if you recall, remember we actually disregard this carry because let's say in the digital memory you cannot save more than 8 bits, so you'll be disregarding the 9 bit. So if you disregard this bit, this number actually becomes positive because of this, because it actually starts with a 0. So it's the same reason. If you add two negative numbers, there is no way your answer can be positive. So if I probably have seen two examples here which actually tells you that in case of addition, these two examples tells you that a lot of times your binary addition will have a wrong answer. Okay, and there is no way actually we can fix it. But what else we can do is, instead of fixing, we can make a circuit that will be a separate circuit, which will be in addition to what we have done in lab 6, on top of what we have done in lab 6. That circuit can tell you whether you had an error overflow or not. You see what I'm saying? So that means even if you cannot fix the answer, you will know that the answer is not correct. You know what I'm saying? Same thing happens in case of subtraction. Again, this is called overflow condition for subtraction. We'll show you some example. Let's look at this example. Let's say you have you are subtracting 128, negative 128 from 64. If you do the subtraction just using the regular math operation, your answer should be a positive number, right? Because it will be 64 minus 120, negative 128, right? 64 minus negative 128, which must be a positive number, right? But if you look at the example here, see the answer is actually negative because it starts with a positive, I'm saying 1, right? So that's a negative number. Again, this is wrong because the sign is not correct. Same is here. You are subtracting you are subtracting 64 from negative 127. That means your answer must be negative. But you see here, the answer came positive because the number starts with a 0. So again, the sign error. So the overflow condition actually means the sign error. That means the answer has a wrong sign, and of course the wrong magnitude. And as I said, we use the binary rules. There is no way we can fix it. The only thing that we can do is we can build a circuit which can detect the overflow condition in case of subtraction and addition. Now, in the next couple of slides, we'll show you some very easy techniques that you can use to identify the overflow condition. Now, here is the technique. In case of addition, this technique is actually for addition. What happens is, to make it simple, we'll be writing the number in hex. Okay, so we perform the hex addition for two numbers at the beginning. So let's say we are given these two numbers, okay, 5C and 6A, and we just do the hex addition, just like how we do the hex addition. Once we know the hex addition, we convert all of these numbers. Let's say the first number is A, and the second number is B, and the summation is sum. Okay, now the summation is represented by this symbol. See this symbol here? This is a Greek symbol which always represents the sum. Okay, now we convert all of this to binary. Now once I convert it, how did I convert? This is actually 5. Look at this, 0 1 0 1. This is my 5, right, in binary. And then this is my C, 1 1 0 0. You can actually use the chart that you have. Those charts are also there in the tutorial section in case you don't have it right now. You can use those charts to convert it. This is 6 0 0 0 1 0 1 1 0, which is 6 from the chart. And then this is A, 1 0 1 0. Now once you add it, you got 6C. Now how do we know that we have an overflow here? This is how we can tell. Again, this is an addition, right? This is how we can tell. If my most significant bit from A and the most significant bit from the B are same. What do you mean by same? Both are 0 or both are 1, okay? But the most significant bit from the sum is different, which is the case here, right? See, the most significant bit is 0, most significant bit is 0 in case of A and B, but for the sum, the most significant bit is different. That means there is an overflow. Because this is impossible that you are adding to positive number and your answer will be negative. Or this is also impossible that you are adding two negative numbers and your answer is positive. So it's very easy. All you have to work with is the most significant bit. Okay? You actually don't even have to look at the rest of the bits. All you need is the most significant bit, which is the bit number 7. The reason we call it bit number 7 because we count from bit 0, right? This is my bit 0, then bit 1, bit 2, bit 3, bit 4, bit 5, bit 6, and bit 7, which is the most significant bit. So only, so the only thing that matters to us is the bit number 7, meaning the most significant bit. And we can identify the overflow condition from bit number 7 in case of addition, just following these 3 steps. Any question? Let's look at some example for subtraction. We pretty much have the similar steps. I'm using two numbers here, 81 and 2b. We'll be subtracting those two numbers. Those are given in hex. Once we subtract, we got 56. I converted those numbers in binary at the right side. Now, how do I detect there is an error? So if the most significant bit of A and B are opposite, but the most significant bit of B and summation is same, they are same, then we can tell there is an error. So that means these two must be different, and this one and the last one is same, are same. If this happens in case of subtraction, then we can tell there is an overflow condition. So it's again the same thing. All you need is the most significant bit. Just from the most significant bit, you should be able to identify whether there is an overflow condition or not. Okay. If you go to the quiz section for this lecture, so what you will see that in every question we actually gave you two hex number, either for addition or subtraction. So you just have to follow these three steps. You have to do the addition or subtraction, get the sum or get the difference, and just convert those two numbers into binary, and just to work with the most significant bit with the numbers. And the answer will be either yes or no, because all we want to know from you that whether the overflow condition occurred or not. Now, if the overflow condition occurred, that means answer is incorrect. You cannot fix it, but you know the answer is not correct. You know what I'm saying? The only difference is we work with the MSB, both MSB, A MSB, B MSB, and summation MSB, but the rules are a little bit different, right, for addition and subtraction. Now, I actually tried to draw a chart here. This chart has information from lab 6. What are the information? If you recall, I know that some of you already finished lab 6 and some of you are in the middle of completing. Remember in the lab 6 there is a switch, right? Remember the move switch? We just move back and forth. The move switch is connected to the ground for doing the addition and connected to the VCC for doing the subtraction. That means this is actually my mode switch, and for all these operation up to here are actually additions, and from here to all these operations are subtraction. Okay, and then remember what do you do in lab 6? We actually have two numbers, right? And we add or we subtract. In case of addition, we add those two numbers. In case of subtraction, we get the sum, get the difference. Now what I did is I actually tried to write all the combinations of those numbers. See, these are only the MSB. As I said, to identify the overflow, all we need is the most significant bit. So this is the most significant bit of the first number. This is the most significant bit of the second number. And this is the most significant bit of the sum or the difference. So I tried to write all the combination, but if you look at carefully, see, these are addition, right? Remember, what is the rule for addition? A MSB and B MSB are same, but the summation MSB is different, right? In that case, you'll have an overflow. So I just wrote it at, I just wrote 1 here because this is an overflow condition, right? Most of those are not overflow, but some of those are overflow. So here again, in case of addition, A MSB and B MSB are same, but the summation MSB is different. Again, overflow, right? In case of subtraction, here are the conditions. A MSB and B MSB are different, but the B MSB and summation MSB are same. Overflow, and this is the last one. A MSB and B MSB are different, but the B MSB and summation MSB are same. Overflow. So you actually have, out of these 16 combinations, can you tell why I have 16 combinations? Because I actually have 4 inputs, right? Remember, if you have 4 inputs, you'll have 16 combination, right? It will be 2 to the power 4, which is 16. So for the 16 combinations, you actually have only 4 rows where you have 1. Here are the rows. This is the one, this is 1, this is 1, this is 1, and this is 1. Now, from this truth table, we can write an expression, right? How do I write an expression? Let's recall, I think we already know how to write an expression, right? We only write the expression only for the row where you have 1, right? How do I write it? what I did is instead of writing A MSB, I'm writing A4 to make it a little bit simple. Instead of B MSB, I'm writing B4. Instead of summation MSB, I'm writing summation 4 just to make it a little bit simple. So what would be the expression for this row? It will be, let's go back here. Look at this, M prime, right? Because it's 0. Then A4 prime, B4 prime, and summation 4, right? That's exactly the expression for this row I wrote here. And for this row, my expression would be M prime because M is 0, right? Then A4, B4, summation 4 prime because it's 0. Same I just did for this and this row, so I just got 4 expressions for these 4 rows, and then I just added all those 4 expressions, sub-expressions, to make my final expression. Now in lab 7, we'll actually build a circuit for this expression. This is the Boolean expression for lab 7. So in lab 7, we have a circuit which we'll be building just for this expression. Okay, for this expression. That means this circuit will be able to tell you whether there will be an overflow or not based on lab 6. So to make it independent, we'll actually build a separate circuit, but as you can guess, in the real situation, this M, A4 and B4, summation 4, all these should be taken from lab 6 to make lab 7. You see what I'm saying? Because in lab 6, you already have A4, B4, summation 4 and switch M. So you can connect those as an input to lab 7 to make lab 7, but instead of doing it, to make it simple, we'll be using a switch. Okay? We'll be using 4 switch. The first switch is for M, second switch will be for A4, third switch will be for B4, and the last switch will be for summation 4. Just to make it simple. Okay? So for this part, we also have a single quiz, which is chapter 2 quiz number 1, which will be actually in sequence. So you should be able to see this quiz after chapter 6 quiz 3. Okay, we are going back and jumping back to chapter 2 because we want to make sure we understand this part of the lecture which is related to lab 7. So again, this is the lecture for lab 7, and this lecture also covers the quiz which is chapter 2 quiz 1. Okay.